In this talk, I will speak about scaling limits of Baxter permutations and some related objects. On the top of the slide, you can see some uniform simulation of these objects that will be clarified during the talk. I will also mention some local limit results. This is a joint work with Mickaël Maazoun from Lyon. Let me start by explaining our point of view on permutation, that is geometric. Consider the permutation sigma that maps 1 to 6, 2 to 2, 3 to 5, and so on. To it, we can associate its permutation diagram. Here it is. And moreover, we can also associate a probability measure in the following way. In each box where there is a dot, we replace this dot with the Lebesgue measure of mass 1 over n, where n is the number of dots in the diagram. In this way, what you obtain here, it's a probability measure that has in particular the following property. The marginals are uniform. A permuton is a probability measure on the unit square with uniform marginals. And the objects that we saw before are permutons. Why do we want to have this point of view on permutation? The reason is because we want to consider limits of permutation. And on the space of permutons, we have a very natural notion of convergence, that is the weak convergence for measure. This space, endowed with the convergence of measure, defines a nice compact polyspace. And in particular, limits of permutons are still permutons, and so their potential limits have uniform margins. Let me explain what are Baxter permutations. These are permutations avoiding the patterns 2, 4, 1, 3, and the pattern 3, 1, 4, 2, with additional requirement that 4, 1 and 1, 4 have to occur consecutively. Let me explain this definition with an example. For instance, this on the right-hand side is not a Baxter permutation because the 4 orange highlighted points are in the same relative position of 2, 4, 1, 3, and moreover 4 and 1 are consecutive. Here, on the left-hand side, we have a Baxter permutation. Indeed, despite we can find 4 points in the same relative position of 2, 4, 1, 3, we cannot do that in such a way that 4 and 1 are consecutive. Why do we want to study Baxter permutations? Douglas and Pax in 2014 explored the expected shape of doubly alternating Baxter permutation. These are permutations such that both the permutation and its inverse are alternating and Baxter. And what they claim in their work is that it would be nice to compute the limit shape of Baxter permutation. Here we can see some simulation of large Baxter permutation, sample uniformly at random. And the goal of the rest of the talk is to investigate what is the limiting object behind this picture. Another motivation to study Baxter permutation is because they are related to many other objects. Punichon, Bousquet-Moulou, and Fusy in 2011 showed that Baxter permutations are in bijection with plane bipolar orientations. These are planar maps equipped with an acyclic orientation of the edges, with exactly one source and one sink, both on the outer face. Let me give you an example. Here we have a bipolar orientation. Here there is the source, here there is the sink, and all the edges are oriented from bottom to top in such a way that there are no oriented cycles. Bipolar orientations are in bijection to Baxter permutations, as we said before. But bipolar orientations are also in bijection with a specific family of two-dimensional walks in the non-negative quadrant. These walks are called tandem walks. This bijection was first discovered by Kenyon, Miller, Sheffield, and Wilson. Building on this bijection, Wayne, Holden, and Soon proved in 2016 that an infinite volume random bipolar triangulation, so a bipolar orientation where all the faces have degree 3, converge in a specific sense made precise in their article to the Liouville quantum gravity of parameter square root 4 over 3. So far, we have seen a bijection between bipolar orientation and tandem walks. and a second bijection between bipolar orientations and Baxter permutations. If we compose correctly these two maps, what we obtain is a bijection between tandem walks and Baxter permutations. Usually, you're very happy if you have such a bijection, because what you want to do is to study scaling limits of tandem walks and then to transfer this result to Baxter permutations. The problem is that in order to study permuton convergence, we need a very good control of patterns on permutations. And usually this is difficult. In particular, given a Baxter permutation, it's very difficult to read a pattern in the permutation from the associated tandem walk. Let me explain this problem more precisely. We consider a tandem walk WT and the corresponding Baxter permutation sigma. And we want to answer to the following question. Given I smaller than j, we want to find a way in order to read on WT if sigma I is smaller than sigma j, or sigma j is smaller than sigma I. The solution that we found is to construct the following family of discrete objects called Coalescent-Walk processes. These are a collection of walks that follows the YT projection of W when they are positive, and the minus XT projection when they are negative. I will explain that more precisely in the next slide. I will not enter in the details of this definition, and I will clarify it in the following example. Here, in the left-hand side, we have a tandem walk, and on the right-hand side, we have the associated coalescent walk process. So in red, we have just the YT projection of this walk, and in blue, the minus XT projection of this walk. Then the coalescent walk process is constructed in the following way. At each integer of the x-axis, we start a walk that, when it's greater or equal to 0, is following the red walk, and when it's strictly less than 0, is following the blue walk, with the following exception. If the green walk is forced by the blue walk to cross the x-axis, then instead of just crossing the x-axis, this green walk will coalesce with the walk that is starting at the same time. If we consider the coalescent walk process associated to the tandem walk that we saw in the previous slide, we have a very natural tree structure, highlighted here in green. In particular, we can consider the contour function of this tree, and we can label through it the black dots in the x-axis. We label the first explore dot with 1, the second one with 2, the third one with 3, and so on. In this way, we determine a permutation that will be denoted by Cp of z. In this example, this is the permutation that maps 1 to 8, 2 to 6, and so on. What we show is that if you consider this permutation or the permutation associated to this tandem walk through the map that we saw before in the diagram, these two permutations are exactly the same. Moreover, what we show is that we have a very strong tool to read patterns here through this structure. In particular, what we show is that given I smaller than j, sigma I is smaller than sigma j in this permutation, if and only if the walk starting in the coalescent process at time I is negative at time j. The first result of the previous slide additionally proves the following theorem. If we add to the diagram that we have seen before the map that gives from a tandem walk a coalescent process, and from a coalescent process the corresponding Baxter permutation, this gives a commutative diagram.
Moreover, what I can say now is that the object that I introduced in the first slide were just large objects related by these maps. Now we move to the scaling limit result. Let me first introduce what is the potential scaling limits for coalescent walk processes. We have to consider a two-dimensional process, WT, and the following family of stochastic differential equations that are indexed by time u in an interval I. So the stochastic differential equation is the following. The process is 0 before time u, and after time u is following the y projection when is positive, and the minus x projection when is less or equal than 0. This family of stochastic differential equation was already studied in the literature with the following result. If the driving motion Wt is a two-dimensional Brownian motion with correlation ρ between -1 and 1 extreme excluded, then this family of stochastic differential equation has pathwise uniqueness and existence of a strong solution. So, in particular, if we consider this family of stochastic differential equation for all u in R driven by a two-dimensional Brownian motion with correlation -1/2, then using the previous theorem and Fubini-Tonelli, we can show that for almost every omega, ZU is a solution for almost every u. And so we define the continuous Coalescent-Walk process driven by W as the collection of solutions ZU for all u in R where they are properly defined. And this is our scaling limit for Coalescent-Walk processes. So let me show this result. We consider a two-dimensional random walk W bar that is starting at time 0 at the origin and with step distribution given by the following expression that is not relevant for our talk. The important fact is that once we condition this walk starting at the origin and to end at time n+1 again at the origin and to stay in the mid-time in the non-negative quadrant, then this walk is a uniform tandem walk of size n. And in particular, if we consider the associated rescale continuous process that interpolates the step of this walk, what is easy to show is that this walk converges to what is called the two-dimensional Brownian excursion in the non-negative quadrant with correlation -1/2. This is a corollary of the result of Denisov and Vashtel on random walking cones. Our contribution is the following additional result, that if we consider the pair given by the walk and the walk starting at u in the discrete Coalescent-Walk process driven by this walk in the discrete version of the Coalescent-Walk process, then this pair converge to the two-dimensional Brownian excursion and the relative solution of the differential equation that we saw before when is driven by this Brownian excursion. Building on this result, what we can show is the following. If sigma n is a uniform Baxter permutation of size n, then we can show convergence in distribution of the associated permuton to a permuton that we call Baxter permuton. And this Baxter permuton is explicitly constructed from the Coalescent-Walk process driven by the Brownian excursion that we saw in the previous theorem.
The proof is based on the following two results that we have already seen. The first one is the fact that we are able to read patterns in permutation from the associated Coalescent-Walk process. And the second one is a slight generalization of the previous result of convergence of discrete Coalescent-Walk processes to the corresponding continuous version.
Let me finish my talk with some final comments. First of all, let me clarify that our results imply convergence of finite volume bipolar orientation to a square root 4/3 Liouville quantum gravity. In particular, this is a generalization of the results that we saw of Gwein, Holden, and Soon. Let me also underline that this convergence holds jointly for the primal and the dual map. This result suggests the following natural question. What is the connection between our approach and the Liouville quantum gravity approach? In particular, do we have a stochastic differential equation encoding on some quantities related to the Liouville quantum gravity? Another point is that the convergence of all the objects, so the convergence of tandem walks, permutations, bipolar orientations, and coalescent-Walk processes all jointly. In our paper, we also proved joint Benjamini-Schramm local limits, both in the annealed and quenched sense, for all the objects that were involved in the commutative diagram. Benjamini-Schramm convergence is a type of convergence that is local in the sense that you have to look at ball of fixed radius in a vertex of your discrete objects chosen uniformly at random. We believe that our techniques that we use to prove this result are rather general, in the sense that we would like to consider many other families of permutation that are encoded by two-dimensional walks, and to show that they converge to a one-parameter modification of this Baxter permutation. So, in some sense, we want to prove that the Baxter permutation is a universal object. And in order to find families of permutation that are encoded by two-dimensional walks, we think that a key tool is to use family of permutation that have been enumerated using generating trees. And recently, I developed a technique to sample uniform permutation in these families using some types of two-dimensional walks. And finally, I think that since we have this new, very likely universal limiting object, it would be worth it to investigate it better, in the sense that we would like to analyze some typical properties of this object. One natural question, I think, is to compute its intensity measure, that is the expectation of this random measure. But I think there are many other natural questions. For example, another one can be to compute the Hausdorff dimension of the support of this random measure. Thank you very much for your attention, and do not hesitate to contact me if you have further questions or comments. And let me finally mention that the full version of the paper is now available on arXiv.